Hi everyone, my name is Osama Yusuf. I am a PhD student from the George Washington University. The topic of my lightning talk today is towards a hardware-aware decomposition method for resistive RAM neural network training. This work is in collaboration between our group at GW and NIST. So artificial intelligence is exploding and has become resource hungry with a lot of modern networks requiring hundreds of thousands of computing chips. There is thus a growing need for faster and efficient neural network accelerators. And even though accelerator technologies have come a long way from CPUs to GPUs to TPUs, they're all limited by the von Neumann bottleneck, meaning they exhibit higher power demands and extremely low energy efficiency at large scales. So the question which everybody's after is what's next? So research has shown that compared to accelerators based on mainstream memories, emerging technologies in specific resistive RAM devices-based accelerators are more compact, faster, and more energy efficient. This is because these devices can combine data processing and storage, essentially sidestepping the von Neumann bottleneck. In the context of neural networks, this means that vector matrix multiplication can be implemented by a crossbar array of these devices. So here's a figure of our experimental setup, which is a chip with 20K Memristive devices. This is still a work in progress, and the current results for this talk are based on simulations. So one challenge hindering resistive RAM technology from going mainstream is that training a resistive RAM network is still demanding. An M by N layer requires M by N units of memory for gradient storage. Advances in low rank decomposition can bring this down to the order of K of M plus N, which for a sufficiently low value of K is quite an improvement. However, in previous work, we observed that different decomposition algorithms lead to different training dynamics. So we're comparing NMF and SBPCA in terms of test accuracy. And as you can see that at similar ranks, they exhibit different training dynamics and training accuracies. So we realized that different algorithms are prone to different challenges. So for example, SBPCA had a lot of oscillatory updates, whereas the NMF algorithm just consistently showed low accuracy at low ranks. So the vision was to identify an optimal hardware-aware decomposition algorithm. And the first step towards answering that question is to basically identify what constitutes optimality. And to answer this, we need to take a further step back. We needed to study resistive RAM-induced training dynamics. And so that's basically what I'm going to be covering in the next few slides. So we use an analytical device model inspired by the Neurosym simulator. Here we're only studying the isolated impact of nonlinearity on training. The conductance trajectories are modeled as an interpolation between minimum and maximum conductances, where the interpolation function alpha is an exponential function of the applied number of pulses and the parameter A, which happens to be a function of the nonlinearity. So as you can see, higher the value of this nonlinearity parameter, higher is the degree of nonlinearity in the set and reset conductance trajectory curves. So let's briefly go over the weight update rule. The software gradient matrix is quantized into a pulse number for delta G, and the software weight is mapped into a conductance value G, which is used to determine an effective pulse number for G. These two blocks together are used to basically obtain the updated conductance, which simulates the application of sequential pulses. So when we have G plus delta G, we use that to derive back or map back to the weight space, which is basically clipped. Now there are two steps that are key here. The quantization and the clipping actually reflect and correspond to the limited precision and the limited dynamic range of these devices, whereas the non-linearity, which is a device non-ideality, that actually manifests in this pulse application step. Right. So in the case where we have zero nonlinearity, i.e. where the set and reset curves are perfectly linear, that would correspond to a device that has no nonlinearity and no non-ideality. And so we would refer to that as being an ideal device model. In terms of the methodology, we're using cropped MNIST, which is basically the traditional MNIST dataset, just the images are center cropped to 20 by 20. The network structure that we have is a 2-layer perceptron network. The dimensions of the first layer are 400 by 10. The second is 10 by 10. We're using mini batch gradient descent with a batch size of 4096. In terms of the parameters, the weight initialization scheme and the learning rate are general network level parameters. The quantization states and the weight range are device level quantization parameters. And then finally, we have the device nonlinearity, which is a non-ideality parameter. And just for fair comparisons, all of the networks start from the same weights with all randomness and sources of randomness fixed for fair comparisons. So the first observation that we have was that nonlinearity actually induces noise. So if we take a look at the convergence curves, firstly, we see that devices actually consistently obtain lower test accuracies compared to the software network. And then the training is actually much noisier compared to the software as well, right? This gap, we actually refer to this as performance gap. I just wanted to highlight that here. We also take a look at the gradient covariance. This is the network gradient covariance plotted at the end of training at different device nonlinearity values. So we see that increasing the nonlinearity essentially significantly increases the variance of the gradient matrix for both of the two layers. The highest increase we see is for FC2, which is 20 folds. In terms of the weight dynamics, here we're tracking the evolution of fixed weights with training across the two network layers, so FC1, FC2. For the device models, we're seeing that as we increase the nonlinearity, the overall noise in these trajectories also increases. What this means is that even with the same initial conditions, the network actually ends up learning different answers to the problem, especially the software network. This specifically piqued our interest into understanding more what's happening differently in the software network compared to these device networks. So based on experimentation and empirical evidence, we found that the network learning rate can balance out noisy gradients. So here we have a plot of what we call the learning window or the training window. In essence, we're sampling different learning rate values and we train the network for a given number of epochs. In this case, it was fixed at 100. And we define the optimal learning rate as being the learning rate value at which the network attains the highest mean test accuracy. So these four markers are basically four different sampled values of the learning rate. We have the corresponding convergence curves here towards the right. So it can be seen that increasing the learning rate shows a clear trade-off between the mean test accuracy and the overall noise in the training or the convergence curve, right? So if the learning rate is lower than the optimal value, which would be these two plots right here, we see that the mean test accuracy isn't the highest. If the learning rate is higher than the optimal value, the training is just extremely noisy and the overall mean test accuracy also ends up dropping, right? At the optimal value, we see that the accuracy is the highest and then also the noise is lower compared to the non-optimal values. And so this is what we want. And then finally, we have a plot of the gradient variance here again, where we're seeing that at the same device nonlinearity, we were able to reduce the gradient variance by a factor of 6 for FC2 and a factor of 2 for FC1, just by optimizing for the learning rate. So we repeat the same experiment across different device nonlinearities, and we observe that the optimal learning rate actually inversely relates to the degree of nonlinearity. Across different nonlinearity values, we see an average of 5-fold reduction in terms of the gradient variance across the two layers by optimizing for the learning rate. Unfortunately, while we did see an improvement in terms of the performance gap, the performance gap actually still continues to exist. And so this raises the question as to why that's happening. So a deeper look at layer weight histograms after training suggests that FC2 weights in the case of the device models are actually getting clipped compared to the software weights because of the limited dynamic range of these devices. We see that approximately 85% of the FC2 weights were clipped. And so this raises the question, is the performance gap a result of this weight clipping? So we try and eliminate the clipping to check if it minimizes the performance gap. In the first attempt, we match the magnitude of FC2 weights with FC1 weights since only FC2 gradients pushed weights to their bounds. We see that this doesn't really help and the performance gap and the histogram still exists and tell the same story. In the second attempt, we basically broaden out the weight clipping range and we see that this does kind of help. The weight clipping is gone. We don't see the weights getting clipped anymore. However, the performance gap actually ends up increasing. And so the hypothesis here is that since the quantization levels were kept constant, pulses are causing a larger weight change. And so it makes sense to investigate what happens at increasing values of the quantization levels or higher precision. So here we have convergence curves at different device nonlinearity values. Column-wise, we're investigating quantization level 100, 500, and 1000. In row-wise, we have the fine weight range, and then the broader weight range. So the overarching observation here is that increasing the quantization states or precision minimizes the performance gap significantly. For Pmax 100, which is the best reported level in devices currently, the gap is quite big in the finer range, but then something interesting happens in the case where we have the broader range, where we lose training altogether. And so the reason for this is that the precision is effectively too low for this particular dynamic range. There is a trade-off there as well. For Pmax 500 and 1000, we see that when we have the finer weight range, we only see a 1% improvement in terms of the accuracy or the performance gap, whereas for the broader range, we see an upwards of a 5% gain in terms of the accuracy. So the observation here is that broader is the weight range, higher is the benefit of increased number of quantization states or increased precision. On a side note, for the finer range, we actually saw that the 85% clipping in the FC2 weights was still happening. And this suggests that maybe the precision actually plays a slightly bigger role than clipping, at least in terms of bridging the performance gap until 90%. So optimizing for the weight clipping range for some available quantization states is important, and we refer to this as being device-aware optimization. So here we use our findings to formulate properties of an ideal decomposition algorithm. The overarching idea is that we would have a training coprocessor that would produce decomposed left and right eigenvectors, which would be used to basically update the resistive array. So the ideal algorithm actually aims to bridge. So the ideal algorithm needs to bridge the software hardware accuracy gap. And for this, it needs to be adaptive, meaning that it needs to take care of device-aware optimization. It needs to be memory efficient. We could do this by imposing sparsity constraints, and perhaps we could gain some information about the optimal level of sparsity by investigating and taking a look at the distribution of weights. Needs to have a low variance in the overall decomposition it produces. And we could perhaps do this by encapsulating the impact of the learning rate through a filtering term in the actual decomposition. And then finally, based on previous work, we know that we also want this algorithm to have streaming construction and support batch operation just for faster compute times. In summary, saw that resistive RAM networks exhibit a performance gap compared to software networks, and that device nonlinearity manifests as training noise. We saw that careful device optimization and using the optimal learning rate can minimize the impact of this noise and then also reduce the performance gap to some extent. We briefly went over some of the challenges with existing decomposition algorithms, and we used our findings to identify key properties of an ideal hardware-aware decomposition algorithm. And then finally, in terms of future work, we could start investigating other device non-idealities in a fashion similar to what we did here, and we can start the actual implementation of the ideal hardware-aware decomposition algorithm now that we know, now that we're aware of the properties it needs to have. And then finally, this is actually a tangent from this project, but an array level update of the entire resistive RAM array is also future work. And this is all I have. Thank you so much for listening, and I'll open the floor now to questions.